Ladies and gentlemen, we're going to go through real quick and just talk about that formative that you guys took on, that was Tuesday now, okay? So if we take a look at this first question, it says a piece of metal, guys, that would be an unknown metal with a mass of 24.7 grams is at a temperature of 100 degrees Celsius, right? And it was dropped into an insulated container of water. Hint, that might be something like a calorimeter. And then the mass of the water was 140 grams, and its temperature before adding the metal, so its initial temperature was 16 degrees. The final temperature of the water turned out to be 17.6 degrees Celsius. What is the specific heat of the metal, and what is the metal based on that chart? So real quick, let's go back through that. We were given the mass of the metal. We were given the temperature of the metal initially. So this is going to be Ti of the metal. Okay, we were given the initial temperature of the water. I'm going to do that in a different blue just to keep them. Actually, let's go ahead and just change the color totally. So let's do that in pink, just so we remember there's a difference. All right, then we have the final, or the mass of the water, which is the 140. If I could write mass or M, man, of water, there we go. And then we were given the final temperature. And so I'm gonna write that in purple. And I'm gonna write that in purple for two reasons, okay? Both of which are gonna be equal to each other. But real quick, let's go ahead and write out that we have water as one object and we have our metal as the other object, both of which we're looking at right now. Okay, so we know that we have four variables always in these problems, or four options for variables. We have Q, M, C, and delta T. Remembering that Q is the energy absorbed or released, M is the mass, C is the specific heat capacity, and T is the change in temperature. So let's fill out some stuff we know. We know the mass of the water, which equals 140.0 grams. Water always has the same specific heat capacity, and it's given to us in the table, which is 4.184 joules per gram degree Celsius, or that means 4.184 joules of energy are required to raise 1 gram of water by 1 degree Celsius. 84 joules per gram degree Celsius. And then we need to remember that our delta T is really our final temperature minus our initial temperature of our water, which means that we have to look at the final temperature of the water, which is 17.6 degrees Celsius minus the initial temperature of 16 degrees Celsius, which gives us our change in temperature of 1.6 degrees Celsius. All right, so that was our water, but we also were given metals information. So we were given the mass of the metal, which is 24.7 grams. We were not given the specific heat capacity for the metal. That's something we're looking for. We weren't given the Q of the metal either, and we were given the initial and final temperature of our metal. So we know that again is our final minus our initial, not our final minus our final. And our final temperature of our metal, because our metal was placed in the water, is the same as the water's final temperature of 17.6 degrees Celsius minus our 100 degrees Celsius for our initial temperature of our metal, which means our change in temperature is negative 82.4 degrees Celsius, because it released that energy. It needs to have a negative change in temperature. So now that we have all the information we needed to start our problem, we can go ahead and look and see that our water is only missing one variable versus our metal is missing two. So we're going to solve for something with our water first. So Q equals MCAT, or Q equals MC delta T. Okay, and we can plug in our information of the mass, which was 140 grams, our C, which was our specific heat capacity of 1.184 4.184, excuse me, joules per gram degree Celsius, and our change in temperature of 1.6 degrees Celsius. Okay, once we do that, we can go ahead and just multiply all those together, and we get a Q is equal to 937.2 joules, or really 937 joules if we're doing significant figures. So that's going to be our Q, which then we need to remember that our Q of water needs to be the same as our Q of our metal. So this, but an opposite sign. So our negative Q of metal. So our Q of our metal is really negative 937 joules, because it has to be equal and opposite, because that's how much the metal released in energy, which is what our water gained in energy. So now we can now plug in our information because we have enough to solve. So again, we're using Q equals MCAT, or Q equals MC delta T. Now we plug in our negative 937 is equal to our mass of 24.7 grams times the specific heat capacity, which we don't know, times our change in temperature, which is negative 82.4 degrees Celsius. We can even multiply together our two numbers and leave our C as a separate entity. So we multiply 24.7 times negative 82.4, and we should get around negative 2,035.28, which is going to be in grams times degrees Celsius, and that's times our specific heat capacity. And then we divide both sides by negative 2,035.28 from both sides to get our specific heat capacity to equal 0.460 joules per gram degree Celsius. And then we check our table. The one that is closest to 0.460 is 0.466, which is going to be steel, which means that our object or our metal is steel. All right, so we completed our first question. Now we have to go back and do our second question. So now this time we were given the fact that our metal is cobalt, and we know its specific heat capacity is 0.418 joules per gram degree Celsius, and that it started at 200 degrees Celsius before it was dropped in our calorimeter, measuring containing 50 milliliters of water, so really 50 grams of water, and it started at 21.1 degrees Celsius. The final temperature of everything was 67.1 degrees Celsius, and we wanted to figure out the mass this time of our cobalt sample. So again, we have our water. I'm gonna do it in the same color. So our water versus our cobalt. So I can leave it as cobalt because we know it is. And we have our Q, M, C, and delta T. And we don't know Q, but we know our mass was 50 milliliters, or 50 grams really. Our C is our specific heat capacity of water, 4.184 joules per gram degree Celsius. And we know our change in temperature is going to be our final temperature of 67.1 degrees Celsius minus our initial temperature of 21.1 degrees Celsius to equal our change in temperature of 46.0 degrees Celsius. Okay, we can also do our cobalt, so we don't know our Q just yet, but we could find that eventually. We're looking for our mass, so that's also blank. We know our specific heat capacity is 0.418 joules per gram degree Celsius for cobalt, and we know our change in temperature is going to be our final minus initial temperature. So it's our final of 67.1 degrees Celsius minus the 200 degrees Celsius it started at, to give us a negative 132.9 degrees Celsius for our change in temperature. Now that we have all that information, we can start by finding our Q of our water. So Q is equal to our mass of 50 times our specific heat capacity of 4.184 joules per gram degrees Celsius times our change in temperature of 46 degrees Celsius to give us a Q value when we multiply those three together of 9,614 joules, or significant figures of 3, it's really 9,610 joules. Remember, that is equal to the negative Q of our cobalt. We have a negative 9,610 joules for our cobalt. And so now when we plug in our information, we plug in our negative Q, or our Q is negative 9,610 joules is equal to the mass, which is unknown. So we leave it a variable, times 0.418 joules per gram degree Celsius times our negative 132.9 degrees Celsius. All right, we can combine our terms on the right side. So negative 9,610 is equal to our mass times negative 55.552. And that's going to be joules per gram. Now that our degrees Celsius have canceled, and we divide both sides by negative 55.552, negative 55.552. And we end up with our mass, which is running out of room. Our mass is equal to about 173 with significant figures in grams. If you guys have any other questions, please let me know. Otherwise, have a wonderful rest of your day.